We spend our lives inside these massive structures of steel and concrete, and we just trust them to stand strong, right? But how can anyone really know? How do you prove a skyscraper is safe before a single piece of steel is even on site? Seriously, have you ever thought about it? It's not magic, and it's definitely not guesswork. Turns out, there's this incredible process where buildings live an entire lifetime of stress and strain, all before they even exist in the real world. So what's the secret? Well, it all starts with something called a digital twin. Think of it like a perfect virtual replica, a super detailed 3D skeleton of the entire building. And then, using some seriously powerful software like the industry standard STAAD.Pro, engineers can basically throw the kitchen sink at this virtual structure. Okay, so how do they even build this digital twin in the first place? It's actually a really meticulous 3-step process, and it's the foundation for literally everything else. First up, they define the geometry. We're talking the exact height, width, and length of every single floor. Then they assign the sections, which just means telling the software the precise shape and size of every beam and column. And finally, they define the materials. They have to be specific, like this is M25 grade concrete and this is FE500 grade steel. Every single detail has to be perfect. Once that virtual skeleton is all built, that's when the real test begins. This is where engineers simulate all the forces a building is going to have to deal with over its entire life. Let's break down the big ones. First, you've got what are called dead loads. These are the constant, never-changing forces. It's just the building's own weight, all the concrete, all the steel, all the glass. It's the baseline stress that the structure is under, 24/7. Next up, you have the live loads. Now, these are the forces that change all the time. Think about all your furniture, your bookshelves, everything. And then imagine you decide to throw a massive party and invite a few hundred of your closest friends. Yeah, the software has to account for all that potential weight. And finally, especially for the really tall buildings, you have wind loads. And we're not talking about a gentle breeze here. This is the powerful, dynamic pressure from high winds pushing against the building. You can imagine, the taller the skyscraper gets, the more critical this calculation becomes. So, just to recap real quick, you've got the permanent dead loads from the structure itself, the temporary live loads from everyone and everything inside it, and the environmental wind loads from the outside. The really key thing to remember here is that the building has to handle all three of these, often at the exact same time. But here's where it gets really, really cool. Engineers don't just test these loads one by one. No way. They test combinations. So what happens on a day with hurricane-force winds while the building is packed to the gills? They simulate these absolute worst-case scenarios to find the breaking point. And even then, they design with a huge factor of safety, which means buildings are built to be way stronger than they'll ever actually need to be. All right, the virtual building is built. The worst-case forces are all loaded in. Now it's time for the moment of truth, running the analysis to see if the design actually holds up. So the software spits out these incredibly detailed reports, but two of the most critical are these diagrams. So imagine you take a plastic ruler, right? The bending moment diagram shows the forces that happen when you bend it, that tension that could cause it to snap. Now, imagine trying to cut that ruler with scissors. That's shear force. It's a slicing pressure. Engineers have to check both to make sure every single beam is way, way within its safe limits. And one final, super important check is for something called nodal displacement. A node is just a fancy word for any joint where beams and columns meet up. This test measures how much those joints actually move under all that pressure. Because, a building that's technically strong but sways a little too much, well, that's not just unsafe, it's also really uncomfortable for the people inside. Okay, so we've gone deep into the virtual model, the forces, and the analysis. Let's kind of zoom out and talk about why this all matters so much in the real world. This whole process, as you can probably tell, demands absolute, total precision. A tiny mistake, like miscalculating a load or even just using the wrong units, say feet instead of meters, can result in simulations that show a complete disaster. In the real world, there is zero room for that kind of error. This quote really gets right to the heart of it. This entire process, it isn't just a technical exercise, it's an ethical duty. At the end of the day, all those numbers on the screen translate directly into keeping people safe. So the big takeaway here is this. By mastering these digital stress tests, engineers are getting the training they need to design the safe, stable buildings that literally shape our world. This virtual training ground is absolutely essential for real-world success. And that kind of brings us to a final thought. The next time you find yourself looking out the window from a high floor, or you're walking through some huge open atrium, just take a second to think about all the invisible forces at play and the incredible digital engineering that's working hard to make sure that structure will always stand strong.